Here's how to boss this simple circuit. First of all, what have we got? We have got a 12 volt battery, shown here. We have got a 6 ohm resistor and an 18 ohm resistor. Is the circuit in series or parallel? Well, we can tell by just following the track. And you can see that it doesn't split up, and therefore if it doesn't split up, it's got to be what we call a series circuit, because one resistor follows the other. Back to the battery, one resistor follows the other. So now we've ascertained it's a series circuit. Now what we want to do is find the potential difference across the 6 ohm and across the 18 ohm resistor. That's what would happen. We put a voltmeter across these particular resistors. But what is happening? This is what's happening. In the battery, each coulomb of charge is going to gain 12 joules. When it passes through the resistor, it gives up some of that energy, and that's what we're going to try and find out. And also going through the 18 ohm resistor, it gives up some of its energy as well. So there'll be a potential difference across the 6 ohm resistor and a potential difference across the 18 ohm resistor. Now we can guess where most of the energy is going to be lost. You guessed right, it's going to be the 18 ohm resistor. The bigger the resistance, the more energy per coulomb is lost, therefore the bigger the potential difference across it. Now to find the potential difference across each of these resistors, we're going to stick to what we call the label method. And what's the label method? We just look at each resistor and we make up a label of V, I and R. V will be the potential difference across it, in other words the energy lost per coulomb across it. I will be the current flowing through it, and R will be its resistance. And we do the same down here. We do V, I and R. And that's just got our labels ready. Now we fill in all the details. Well, we know the value of the resistor here is 6 ohms, and we know the value of this one here is 18 ohms. But we've got nothing else. But we can find the current going around the circuit. And how do we do that? Well, we find the total resistance. And since it's a series circuit, the total resistance is just going to be equal to the first resistor plus the second resistor, which is going to be 6 ohms plus the 18 ohms. And that's going to give us a total of 24 ohms. So now we have got the total resistance of that circuit. And if we have the total resistance of the circuit, we can find the current going through it by using the battery voltage. So if the current passing through that circuit I is going to equal to V upon R, which is going to equal to V, the voltage, 12, divided by 24 ohms, and that's going to give us a current of 0.5 amps. So now we've got the current, we fill that into our labels. So the current here will be 0.5 amps, and the current up here will be 0.5 amps as well. Now look, we've got V, I and R, we've got 2 things out of 3, we can find the third. In this case we can find the potential difference V, which is going to be dropped across each resistor. And to do that we just use the simple equation. We'll do our equation work here. V equals IR. That's going to equal to 0.5 times 6, and we now know it's going to be 3 volts. So right away we can fill that in up here. We know that the coulomb of charge going to pass through that resistor is going to lose 3 joules per coulomb. We're getting to know this circuit. And the same thing happens down here. We know that the equation is V equals IR to give us the potential difference, and it's going to be equal to the current, which is the same, 0.5 amps, multiplied by the resistance, which is 18 ohms. That's going to give us a value of 9 volts, and therefore the potential difference across this resistor is going to be 9 volts. So there's the circuit all labelled out for us. We are in complete control of the circuit, we're bossing it. We can answer any questions about that circuit. We can say that each coulomb of charge as it passes through the battery is going to gain 12 joules per coulomb. When it passes through the 6 ohm resistor, it's going to lose energy, electrical energy, and it's going to lose 3 joules per coulomb. In other words, the potential difference is 3 volts. When it passes through the bigger resistor, you expect it to lose more, and it does. It's going to lose 9 joules per coulomb, and therefore 9 volts will appear across the potential difference across that resistor. Now the good thing also is that the energy should add up. If we're given originally 12 joules per coulomb, 12 volts, then we should have 3, and we should have 9, because the 9 and 3 add up to give you 12. The energy is conserved. So that's what I mean by bossing an electric circuit. And the key to it is finding the total resistance of it, finding the current flowing through it if that's asked, and then putting the labels beside each resistor and working out the missing term in those V, I or R. Here we have another circuit to boss. It's a much more complicated circuit because it's got a serial part and it's also got a parallel part. We've got two resistors in parallel, 18 ohms and 18 ohms, only if we close that switch here. If we leave the switch open, then that 18 ohm resistor just simply disappears. So our job is to find the potential difference across the 6 ohm resistor and across the points X and Y. First of all, when switch S is open. Well, when switch S is open, we have this situation here. We can simply blank that resistor out like that. And then we do our usual. We go and make up our labels. So the most important thing is make up the labels for each resistor. V, I, and R for that resistor. And this resistor will take down here and go V, I, and R for that resistor. We can start to fill things in. The resistance of that one is 6 ohms. The resistance of this one is 18 ohms. We've got to find the current in the circuit, but to do that we've got to work out the total resistance of the circuit, and we do know that it's a series circuit now because there's nowhere else for the current to go when that switch is open, and therefore the total resistance can be found by just simply adding up the resistances 6 ohms plus the 18 ohms. And that's going to give us a resistance of 24 ohms. Now we also know that we can find the current now, because the current I is going to equal simply V divided by R. And the V is 12 volts divided by the total resistance, which is 24. That's going to give us a current of 0.5 amps. And that will be the current which is going to be around all the parts of the circuit. So we can fill that in. The current passing through this resistor is going to be 0.5 amps. The current passing through this resistor, 0.5 amps. And you can see now we can work out what the potential difference across each resistor is by using our equation V equals IR, which equals 0.5 times 6, which equals 3 volts. Just wait a minute. In this resistor, we're going to lose 3 joules per coulomb. In other words, the potential difference across that resistor is 3 volts. Now we can do the same calculation down here. V equals IR, and we know the current is 0.5, and we know the resistance is 18 ohms, and therefore the potential difference V across that resistor is going to be 9 volts. So we can put that into the labels there, 9 volts. Now if you look very closely, we have got a complete set of results for each resistor. We know everything about it, or in other words, we've bossed that circuit. We can say that at the 18 ohm resistor you will have a potential difference across that of 9 volts, a current passing through it of half an amp. If you look at this resistor up here, you can say that the potential difference across it, that's if we put a voltmeter across it, will register 3 volts. In other words, the battery gives us 12 joules per coulomb, each coulomb, and each coulomb of charge going through the 6 ohm resistor will lose 3 joules, and each coulomb of charge going through the 18 ohm resistor will lose, in this case, 9 joules. And notice we add up to give us the voltage of the supply. Each resistor's potential difference adds up to the voltage across the supply. Now, what's going to happen when we actually close that switch? Well, if we take away the diagram now, and if we close that switch, then what we're going to have is 2 resistors in parallel, an 18 ohm and an 18 ohm. And there's a hack for that. If the resistors have got the same value and they're in parallel, and there's only 2 of them, then the combined resistance across XY is just simply going to be half of that, 9 ohms. So we can replace that parallel part with just simply 9 ohms. So I'll put in the new value of the resistance. It's just going to be 9 ohms, because we have 2 18 ohms in parallel. So now we've got, in this case here, another situation. We've got a new circuit. We've got 6 ohms and 9 ohms instead of the previous one. So we can do the calculations again. We can work out the new total resistance, and we can work out the new total current. That's quite easy to do, because the total resistance now has changed. It's going to be 6 ohms plus the 9 ohms, which is going to give us 15 ohms. Now we've got the total resistance of the circuit, we can work out the current flowing all round the circuit. And that's simply found by I equals V over R, which is going to be 12 divided by the new one, 12 divided by 15, And if we do that in our calculators, we get the following result. 12 divided by 15, and that's going to give us a current of the following. 12 divided by 15, that's going to give us 0.8 amps. So 0.8 amps are flowing through that circuit. So now we can make a different label for this resistor. It's going to change now. We can put down V, I and R. And we know the current flowing through it is going to be 0.8 amps this time. And we know the resistance is going to be 6 ohms. And likewise down here we can do another similar one. We can do V, I and R down here. And we've got a new resistance of 9 ohms. We've got a new current which is going to be 0.8. And we're now in a position to work out the new potential differences across those resistors. So in this case here we've got V equals IR, and we can put in then the new current, 0.8 times 9, and we do that in our calculator, we get 0.8 times 9. That's going to give us a potential difference of 7.2 volts. So now we can put in there 7.2 volts. And the new one up here, we can do the same calculation again. V equals IR, which equals 0.8 times 6, which is going to give us a value of 4.8 volts. So now we have 4.8 volts across the new combination, and we've also got 7.2 volts across here, and both of them, 7.2 and 4.8, add up to give you 12. So that's the situation we've got when we change things. And you can see what happens when we change things. We've completely bossed that circuit now. We know that when we had a current of 0.5 amps through it, the potential difference is going to be 3 volts. But now we've got a bigger current passing through that resistor. We've got a bigger potential difference, 4.8 volts. And that makes sense. The more current passing through the resistor, the more coulombs are passing through it, therefore the more energy is going to be lost. And likewise down here, originally we had a 9 volt potential difference across that resistor, but once we switched on to the circuit with the parallel part, the resistance became less and therefore the current increased. And as the current increased with the new resistance, you got 7.2 volts here. So that method is called the label method, where you can actually see things changing and you can actually see how it affects the resistance and the current of the circuit. Now here's the label methods or bossing a circuit applied to an internal resistance question. You can see in this circuit here we have got a battery of EMF 1.5 volts and we have an internal resistance of 2 ohms. And how do we know that? Because it's all enclosed in this dotted box. That means everything inside that particular battery. Outside the battery, attached to the terminals of the battery, is a resistor of the value of 13 ohms. Now what we're required to find in this question is we're required to find the lost volts and also the terminal potential difference. Now we know there's an equation for that, we know that, but if you stick with the label method and you know what you're looking at, then it's just easy to do. For example, we go to the 2 ohm resistor and we put down V, I and R. So there's your labels there. We go to the resistor outside the battery connected to the terminals and V, I and R. And we do know that the V in here is going to be the lost volts. That's going to be the potential difference dropped across the internal resistance. That is the lost volts in there. And we know also out here the potential difference across the outside resistor, or the load resistor as it's called, is going to be the terminal potential difference. So there we go, we've identified right away from our labels all the different sort of kind of parts of that circuit. So now what we do is just do the same thing we did the last time. We've got to find the current flowing in the circuit. Because we can do that, we can find everything else. We know the resistance up here, the internal resistance is 2 ohms, and we know this resistance here is 13 ohms. Okay, let's work out the total resistance of the circuit. That's quite simple to do. The total resistance of the circuit is a series circuit because the current is nowhere else to go, and it's going to be just simply 2 ohms plus the 13 ohms. That's going to give us a value of 15 ohms. Once we've got the value of the total resistance, we can go ahead and find the current flowing through the circuit. The current equals V divided by R, which is going to be equal to 1.5 volts divided by 15 ohms. That's going to give us a current of 0.1 amps. So now we know the current flowing through the circuit. The current flowing through the circuit is 0.1 amps. And down here it's going to be 0.1 amps. So what's going to be the lost volts? Quite simply, V equals IR for this label. V equals IR, because V here, the potential difference in this resistor, is the lost volts. So it's going to be equal to 0.1 times 2, which is going to give you a value of 0.2 volts. So we now know that the lost volts is 0.2 volts, and we can put that in our label. What about the down here? Do the same thing again. V equals IR, but this time the labels tell us that V is the terminal potential difference. That's the potential difference available at the terminals of the battery. And that's going to be 0.1 times 13 ohms, which is going to give you a value of 1.3 volts. So we now know that the terminal potential difference is 1.3 volts. So let's look at the circuit again, because we've completely bossed it. We know we've got an EMF of 1.5 volts. We know we've got an internal resistance of 2 ohms and an external resistance connected to the terminals of 13 ohms. We know that the potential difference across this resistor here, the internal resistance, is the lost volts. That's the energy per coulomb lost as the electricity tries to get out the battery. And we know this resistor here is the load resistor, the external resistor. It's connected across the terminals, and therefore the potential difference across it will be the terminal potential difference. And look, the EMF E is 1.5 volts, which means 1.5 joules per coulomb is given to 1.5 joules is given to each coulomb. And the internal resistance, you're going to lose 0.2. And therefore, what's available at the terminal is going to be 1.5, take away 0.2, which is 1.3, which is exactly what we worked out there. Now, we could have done that by using the equations of the internal resistance and all that, but it's better to know the circuit, to understand what's happening in the circuit, to use the label method to boss the circuit, so as you can see at a glance the voltage, which really is the energy lost per coulomb, to know the current and to know the resistance in the circuit. And what's more, if we're given a question like, say the 13 ohm resistor was in fact increased to 20 ohms, we'd know that if you've got an increase in resistance, you have got a decrease in the current. And you just go to the lost volts and say increase in resistance means the current's going to get smaller, and therefore V equals IR, you're going to get smaller lost volts. Therefore, you're going to get more available at the terminal. So that's a method to try out yourself. You can practice it and see how that goes.